Hey guys, how's it going? So today actually we're gonna be looking at principal component analysis. So PCA is a widely used technique in data science, especially when it comes to reducing the dimensionality of the data. So what comes to my mind is that the reason we might want to reduce the dimensionality of the data is that certain algorithms, especially distance-based algorithms, um, they face the challenge of high dimensionality case. So because of this case, reducing the dimension of the features and bringing them to a lower dimension can significantly improve the performance of these algorithms. So hence it is important to use PCA in this case. So for those who are new to the concept of PCA, you can think of like we're reducing columns or features. We probably had something like 200 columns and we're bringing them to probably 10. We do this in such a way that we don't lose the variant or information of these features that are captured inside here. Okay, so that's pretty much the idea. So you can imagine that after you do this, especially if you're someone who's concerned about the performance of the algorithm in production, this can significantly improve the performance of the model towards making predictions, right? The second reason that comes to my mind is that we tend to visualize data, right? You can imagine that you are working on a clustering project and you want to visualize the clusters. But the problem is that you can't visualize the clusters because you had high dimensional data. So reducing the dimension to probably 3D or 2D, then this is actually going to help you to kind of like be able to project your data into like lower dimension, like 2D. Then you can be able to see those clusters and probably this was an image of a t-shirt, probably this was an image of a shoe, something like that. And you can see how these clusters varies from one another. So it's quite good also to reduce the dimensionality of the data so that you can visualize it. Okay, cool. So like we said, guys, that we want to project like m columns into like a subspace of fewer or m columns. So like we need to take a specific set of specific steps to kind of like reduce our dimensions. So the first thing that we're gonna calculate the mean from our data set. So you can think as we have columns, it could be price, it could be quantity, right? It could be anything literally. So we just have to calculate the mean of each column. So we can calculate a mean. So we're gonna use this mean to subtract from each row. Rather, let's say here it was 10, it was 15. So we're gonna subtract the mean from this. So one question might be, but why are we doing that? So we want to center the values in each column. So you can imagine that if we had something like 10 meters, right? So which is equals to 0.01 kilometers. So now we're going to have different scales on the data set. So we want to make sure that the data is on the same scale. That's why we had to subtract the mean from each values in the column. But that's the first thing that we have to do, right? Okay, now that we have centered the values in each column by subtracting the mean, so we're gonna have to look at another concept called covariance. So covariance, before we kind of like explain it, I just want to explain to you another concept called correlation. Especially we use correlation, especially when we want to kind of like calculate collinearity between features. We tend to use correlation. So correlation essentially calculate the direction between two features. So whether the two features are positively correlated, we can think of we have height and we have weight. So this enable us to know the correlation between these two features. So The reason I have to tell you this is because correlation, it's a normalized version, whereas with covariance this is an unnormalized and more of a generalized approach. So we not only looking at two columns, but we can look at multiple columns. So that's why covariance in this case of PCA is more important, because we have more features. So just to kind of like give you an explanation, so we can look at variance as we try to understand how a random variable is, like a random variable could be weighed, how it varies from its own mean. So when we look at core, which is covariance, we're looking at two random or more columns that varies from one another. It could be height and weight. So by calculating this covariance in our problem, we do what we call a matrix covariance. So we're going to calculate covariance on our matrix. Then this is going to give us a score of how each column is, of the covariance of each column against other columns, so to speak. So we're going to look into that when we're writing the code. So now we're going to go to step 3. So remember that 95% of the variance within the data set can be explained with 3 components, right? If we were coming from 200 features, so we can reduce this to 3 features, which are actually explaining 95% of the variance from the data set. Okay? Knowing this in mind, then I'm going to introduce a new concept called Bayesian composition. Okay, so Bayesian composition, we can think of it as we try to find the direction of the maximum variance. So it actually help us to locate the direction of the maximum variance. Yep. So with that in mind, this concept gave us 2 components called Bayesian vectors and Bayesian values. So Bayesian vectors, you can think of it as the directions or components from the reduced subspace, right? So whereas with Bayesian values, we can think of this as it gives us the magnitude of these directions, like, right? So it gives us the magnitude of these directions. So I think now with that in mind, we're gonna get into the code and we're gonna write all of this from scratch, and you're gonna be able to understand. If you didn't understand some of these concepts, it's okay. I'll try to explain everything in the code. I think that way you might actually be able to understand, because you're going to be able to see the outcomes. So that might solidify your understanding. So let's jump straight into the code and try to understand this. Okay guys, let's try to implement PCA. So the first thing that we're going to do is that we're going to actually import Numpy as NP. And then we're going to have our data set. So kind of like cleanse it. So like I said, step number 1 is to calculate the mean, right? So we're gonna say calculate the mean. So to calculate the mean, we're gonna have to take in the np dot mean. We take our data set, then we transpose it, then we say x is equals to 1. So this is gonna be called m. Okay, so kind of show you how the data looks like. Perfect. So because of we have 3 by 2 dimension, so we have 2 columns, so we can think of it as the first column mean, the second column mean, right? That's what we said also. That's what we're gonna do. Now that we have a mean, subtract the mean from the data set. So we're gonna have to subtract the mean. So we're gonna call this probability C. We're gonna take the data set and we're gonna subtract it by the mean. So this is gonna give us our new data set. So we have subtracted the mean from each value in our data set. So the third step we're gonna do is to calculate the covariance. So so to do that, we're gonna have to call this V. We're gonna say np.curve. We're gonna give it c.t. Yeah, c.t, I think. Then this essentially is gonna give us the covariance. Then the first step that we're gonna do is to calculate the Asian vectors, Asian compositions, I think, which is gonna give us the values and the vectors. So the values are gonna help us to rank the vectors. So we can have values, we can have vectors. They all gonna come from linear algebra function. I think it's gonna be np dot linear algebra dot Asian. Then we're just gonna pass in the v, I think. Then the final step is to project the data. So we just have to project the data. So I think we pretty much, that's all it's in it. So it's not really complex to write. So we're gonna say P equals to, we're gonna take the vectors dot transpose dot, then we're gonna take them the vector that we subtracted the mean from, which is gonna be c dot t. So we projected the data. So that's all is into the PCA function. So I hope you guys learned a lot. If there's something you want me to kind of like lecture on, just let me know. That will be great. Anyway, thanks guys for tuning in. See you next time.